All right, everybody, welcome back to our continuation of this example where we're looking at the titration stoichiometry between the titration of acetic acid and strong base sodium hydroxide. We are now on the third part of this question where we are asked to find the pH once we have added hydroxide to our mixture. So we've got our little sample of acetic acid. So let's remember that our concentration of acetic acid initially is 0.040 molar. And we are also going to remember that the initial volume of our sample was 50 milliliters. All right. So I'm going to write out what's going on in the beaker. So let's think about what's going on when we add hydroxide. The addition of hydroxide causes a reaction with the acid. Because remember, our weak acids HA are proton donors. And because OH is such a strong base, we consider this to be a full and complete reaction. So we have now HOH, or liquid water, and then the conjugate A minus. So what this means is that some of our acetic acid, there we go, is going to be reacted away or neutralized by this hydroxide. So let's figure out how much. How much? Okay, I'm going to go ahead and write out this reaction that exists between acetic acid and the hydroxide ion. Again, I'm writing out net ionic neutralization equations here, so I'm not considering the sodium. So when this acid is allowed to do what it does, meaning when it's allowed to donate a proton, be an acid, we create the acetate ion. And then we also create H2O liquid. And let's figure out the stoichiometry here. So we've got a couple of things that we need to consider. So we have to figure out how many moles of hydroxide we added, which will tell us how many moles of acid that were neutralized in this reaction. And why is this something we care about? Remember, going back to our titration curve analysis from the other day, where we were looking at why titration curves are shaped the way they're shaped, we know that as soon as we start adding our base, we are creating more and more and more of our conjugate base, the acetate ion here in this example. And once you have your weak substance and its conjugate present in the beaker in relatively similar qualities, or at least within 10% of one another, that's when we are a buffer. So we need to figure out now the moles of acetic acid made, because the fact that we have HA, acetic acid, and A minus in the beaker together, acetate ion, this means we are a buffer. So we can use our pH via the Henderson-Hasselbalch equation. So we have some stoichiometry to do here. Let's start with the moles of base added. So in that 5 milliliters of sodium hydroxide, let's first convert that volume to liters by dividing by 1,000. So that is 5.0 times 10 to the negative 3 liters of hydroxide. And we want to figure out how many moles that means we added. We know that our hydroxide concentration was 0.1. I think I added a sigma here, 0.10 moles per 1 liter. So this is making this 10 times smaller. This becomes 5.0 times 10 to the negative 4 moles of hydroxide added. All right, so we've got this. Now let's go ahead and think about what this means for the moles of acetate ion, the conjugate that are made. So looking at this neutralization reaction, if I have this amount of moles that I've added, I could figure out how many moles of this are made, assuming that this is the limiting reactant. So maybe we should prove to ourselves that that's the limiting reactant first and start with our acetic acid. So let's think here. Do we have moles of acetic acid in the beaker? I believe we do. Let's go back here. We know that we have this many moles to neutralize. And the question is, did we supply in this 5 milliliters enough moles to neutralize it? Going back to our original calculation, we predicted we needed 20 mils or 2 times 10 to the negative 3 moles of acetic acid and moles of hydroxide present. That is significantly larger than the amount of moles that we presently have added. So we do indeed know, since we've added less than the equivalence volume, that since the hydroxide is the limiting reactant, this is going to determine the amount of conjugate made. Here are acetate ion, and this is made in a 1-to-1 ratio. So we could write that out. 5.0 times 10 to the negative 4 moles hydroxide. And then for every 1 mole of hydroxide added to this reaction vessel, 1 mole of acetate ion or conjugate is made. So that is 5.0 times 10 to the negative 4 moles of acetate. And then we now have to figure out how many moles of acid were neutralized. And then from there, how many are actually left in the beaker. So remember, this neutralization here is all 1-to-1-to-1, right? So if I added this amount of limiting amount of hydroxide, this number, that reacted in a 1-to-1 ratio with our acid, meaning 5.0 times 10 to the negative 4 moles of acetic acid were neutralized. So this is a 1-to-1 ratio again. Therefore, 5.0 times 10 to the negative 4 moles of acid were neutralized. And the question is, how much of this acid remains? So let's go back to our original calculation involving some of our mole quantities in our beaker. So we have here, number 2, how many moles of acid are in this reaction flask? So this was our 2.00 times 10 to the negative 3 moles. So remaining would be 2.00 times 10 to the negative 3 minus 5.00 times 10 to the negative 4. So let's go ahead and do that. Okay, this gives me 1.5 times 10 to the negative 3 moles of acetic acid left. And why did I need the amount left? Remember, we are going to find the pH using the Henderson-Hasselbalch equation because we now have conjugate base and acid in the beaker in similar-ish quantities. So I'm going to go ahead and write out the Henderson-Hasselbalch equation. pH is equal to the pKa plus the log of the proportion of concentration of conjugate, here the acetate, over the concentration of acid, acetic acid. And I'm going to be a little cheap and lazy. I'm going to recognize that I could do a fraction of moles instead of molarity because both of these quantities of acetate and acetic acid exist in the same 50 ml beaker. Sorry, it's not just 50 ml beaker, 50 mils of solution that originally existed, plus now the 5 mils of hydroxide added on top of that. So like this is a new V of 55 milliliters. However, in that same 55 mils, I've got both my conjugate and my acid. So concentration doesn't need to really be expressed in terms of molarity. I could do it in terms of mole because I would have moles over some liter over moles over some liter, which would cancel. Okay, this is going to require us to figure out not just the acetate amount and the acid amount left in our beaker, but also now the pKa of acetic acid. So remember, pKa is the negative log of the Ka. So this is negative log of our Ka of our acetic acid, which going back was this 1.8 times 10 to the negative 5 number here. All right, so 1.8 times 10 to the negative 5, and then we're going to take the negative log of that. All right, this gives me a pKa of 4.74 sub 5. So now my pH is going to be my 4.745 plus the log of conjugate over original. So 5.0 times 10 to the negative 4 moles over my 1.5 times 10 to the negative 3 moles. I do not expect to see a huge change in my pH here because I have pretty small amount of my conjugate that's been made. So let's see here, 5.0 times 10 to the negative 4 over our 1.5 times 10 to the negative 3. Okay. When I do this, this gives me a pH of 4.267 or 4.27 with rounding. So again, if we were asked to find the pH, I have done so, but I've done so using the Henderson-Hasselbalch equation because I am now a buffer. Okay, so we've considered a few points in our titration analysis. We've looked at, before we even begin the titration, what we think we need to add to neutralize all this acid. Then before we begin the titration, how much of the actual H3O plus hydronium ion is present. That gives us an initial pH of our prepared sample of acid. And now we have added 5 mils of hydroxide. We notice that our pH has not changed that much from initial, right? 4.7 compared to 3.07. But let's now see what happens when we add 10 milliliters. So we will do a very similar analysis as we did with 5 milliliters in our next video coming up.